Hello, everyone. My name is Keith, and I'll be presenting a very important topic titled Moisture and Dust in Motion, the dual role of integrated vapor transport over West Africa. Why IVT is important? IVTs are important because they are corridors of enhanced moisture transport, and we can actually view them as the tropical counterpart of atmospheric rivers. Even though in West Africa, we don't have a phenomenon called an atmospheric river or atmospheric rivers, but we can classify IVTs as a counterpart for that. And why is this actually important? IVTs are important because they can do two things simultaneously. Number one, they can transport large amounts of moisture inland, which can trigger intense rainfall and flooding. And also, they can influence atmospheric dust by promoting wet scavenging and redistribution, and also dry and wet deposition of dust. And we classify IVTs into moderate, strong, and extreme classifications. And apart from being classified, for an IVT to occur, it has and must persist for more than 24 hours. If it's less than 24 hours, it's not classified as an IVT. But if it's more than 24 hours, it's classified as an integrated transport. Looking at the left plots, we can see the monthly number of IVT days above the detection threshold. And on the right hand, we can see the monthly mean of 48 percentile IVT intensity, which represents stronger transport conditions. And the message here is that clear monsoon season signal. That means that there exists a very strong signal within the monsoon period. And from June to September, IVT frequency and intensity increased strongly, with maxima along the Guinean coast and the Sudano-Sahelian belt. Even though some locations record up to 30 IVT days, which means for every single day, we can establish the occurrence of IVT during August and September. And if you look at the daily IVT time series, we use this to actually pick up the particular days where we have extreme events. So in June, we have extreme events in June 16, on June 16 rather, June 18 rather, and it's a sharp short-lived spike. And if you look at August, we have another extreme in August 16, and it's still the most sustained event and strongest event, which is very, very, very strong. And if you look at September 25, we have a late season intense surge, which also we can attribute that to a strong vertical coupling during this period. And looking using those extreme dates, we did some kind of a lead lag spatial evolution. That is a day before June 18 and a day after June 18, also for August 16 and September 25. And the main feature is that there exists like a form of an elongated moisture transport plume, which is typical of organized IVT structure. And for June 18 and September 25, we can see an intensification, which occurs over Senegal and southern Mauritania, followed by a westward movement and weakening after the events. That is, if you look at September 26th. So and for August 16, we can see that the course shifts further east over Niger, showing that high VT location changes with seasonal monsoon dynamics and the positioning of the Africa easterly jet. Looking at the response of high VTs to precipitations, on the left, you can see the percentage of rainfall linked to IVT days. And on the right hand, we can see the mean rainfall amount during those IVT events. The first thing you can notice there is that moderate IVTs are the main rainfall backbone of the Guinean coast, and they account for over 60% of the daily rainfall in places such as Liberia, Ghana, and southern Nigeria. In other words, whenever IVT occurs, it accounts for 60% of the rainfall during that period. So as IVT intensity increases, the rainfall belt shifts northward into the Sudano-Sahelian zone. And the strong gravity is actually delivered rainfall surges into northern Nigeria, Burkina Faso, and Mali. And if you look at the extreme IVT, we can see less frequent, but it's more spatially localized. And this actually produces the most intense burst of rain you can imagine, which can lead to extreme flood. So if you look at the interaction with dust, we see that on the left, dust scavenging efficiency increases from May to September, and it peaks in August and September. And this peak coincides with the highest IVT activity. And during the dry season, IVT activity is weak, so scavenging is low, and HOD remains higher. So dust stays airborne longer due to limited rainfall removal. And if you look at the right-hand side, dust removal increases with IVT strength and peak around 300 kilogram per meter per second. But scientifically, this suggests a non-linear threshold. And beyond this point, stronger moisture transport does not guarantee more dust removal. So some of the limiting factors that can guarantee more dust removal includes rainfall efficiency, the cloud microphysics, wet deposition processes, and some other limiting factors. But IVT acts as an important seasonal cleaner of the West African atmosphere. So it can clean up the West African atmosphere during seasons, especially during the monsoon months. So how does it interact spatially? So we can see that along the Sahel, on the left-hand side, along the Sahel from 10 to 15 degrees north, the correlation is strongly negative. That means when IVT becomes stronger, the surface dust concentration decreases. The reason is that the IVT events bring moisture clouds to rainfall, which remove those dust particles from the atmosphere. And also convective downdrafts and mixing can also redistribute dust in the vertical atmospheric column. And if we look at the Guinean coast, the relationship is quite positive. Here, strong IVT often occurs together with heavy rainfall systems. And local aerosol transport, so the signal is more mixed, kind of. And if you look at the right hand side, the red contours mark extreme IVT zones, while the blue shading shows dust wet deposition flux. For June, strongest deposition occurs over the Guinean coast. And for August, the deposition zone shifts northward to around 10 to 13 degrees north. And if you look at September, the IVT bands becomes very narrow, but deposition hotspots remain over the Guinean region and central Mali. Well, this means that IVT do not or only control the transport moisture, but they also determine where dust is washed out of the atmosphere and where we can have cleaner air conditions, which might actually like to occur. So in conclusion, IVT peaks between June and September, and IVTs are not passive moisture corridors. They are vertically coupled systems with deep ascents and have associations with the Africa easterly jet and the tropical easterly jet. And also, if you look at the rainfall, the rainfall rate depends on intensity, actually. Moderate IVTs sustain widespread coastal monsoon rainfall, while the extreme IVT generate intense and localized Sahelian bursts, which actually can lead to flooding. So also if we want to look at the implication of this, the IVT percentile plus AEJ can serve as seasonal rainfall predictors. It can enhance the prediction of rainfall. And also, if you have a real-time IVT monitoring with just nowcasting, it can also serve as a silent corridor guidance for weather forecast. And also advanced IVT parameterization in regional climate models or even global climate models can help our forecasting models and our forecasting technique and also our forecasting outputs. Thank you so much. This paper can be seen from my HOSID link, and many thanks to Roloff for this opportunity, and also many thanks to all my collaborators for contributing to this work. Thank you.